Well, I enjoy the opportunity to be at this conference again. William Bond, whose name is Asterisk, is in the audience, and he'll be in the geometry roundtable. And if you have other questions that I can't get to about how we implemented a Euclidean geometry course, then you could always ask him in that session. I'll be in other sessions learning about something else that I haven't done yet. What I'd like you, I think you probably are quite familiar with Immanuel Kant's point of view with regard to inquiry-based learning, that knowledge begins with the senses, proceeds to understanding, and then ends with reason, and there isn't anything higher than reason. So what I'd like you to take away is my interpretation of David Clarke's rediscovery of geometry as what it always should have been and was for 2,000 years. And our class, let me back up there again, our class structure, it's a modified Moore method course, maybe heavily modified, and then what the student reaction was to the class structure. So you know about the book because you heard about it earlier today. And the audience at UAB is, I think, the kind of audience that Dr. Clarke had in mind. These are largely mathematics majors. In fact, almost all of them were mathematics majors. There was one engineer. They had no previous proofs-based course. There were a lot of pre-service high school and a lot of pre-service middle school math teachers there. And there were a couple of students there who were taking it at the graduate level for a Master's of Education. So for them, we did something a little bit different. I think that Dr. Clarke spoke about the dilemma, the pedagogical dilemma, based upon do we do Euclid's axioms or do we do Hilbert's axioms? And the answer is, well, really you probably shouldn't do either one. You should do a modern geometry, but not so far down as Hilbert. And what do I mean by far down? I brought something with me from Gainesville, where I got my PhD, and that is a gestalt point of view about both perception and understanding. You are probably familiar with the figure here. How many of you see a young woman? How many of you see an old woman? Now, can you see the other one? So this is what you attend to. You're aware of certain things in the figure, but that awareness sometimes can be changed. In fact, sometimes has to be changed. And so I really actually see your point of view, Dr. Clarke, in these terms as what's figure and what's ground. And so I'm going to give a couple of illustrations of that. So first of all, in the ground in nearly all mathematics courses is naive logic and set theory. We only take that out of the ground occasionally. In the ground for a geometry course, following Dr. Clarke's notes, is non-triviality, betweenness, intersections, in fact, the first 8 of Hilbert's axioms about. And what's brought then into the figure is a transformational understanding of congruence that is arrived at by reinvention. The idea that definitions make things definite, and we can work with those. Constructions with straight edge and compass. Remember what Kant said about the senses, leading to understanding and then to reasoning. And then the axioms of plane geometry introduced as needed, and theorems and proofs. So how did we structure the course? Well, first of all, remember I said there's no previous experience in proof-based courses. On the other hand, our capstone course in the mathematics major is a thoroughgoing, slightly modified Moore method course in analysis that lasts 2 semesters. And that's institutionalized in our department. So that course is always taught that way. We do not have a methods of proof course. And we've debated that many times. What we decided to do, or what we have decided to do, is to see if this geometry course can be the methods of proofs course for those who have had no previous introduction to proofs. So early in the course, because we wanted it to be kinder and gentler, there'd be a brief instructor introduction of a topic. The students would work collaboratively in groups. The groups were randomly assigned. Then we would process their work as a whole group, that is, have a whole group discussion. The students were sent home with some homework to further advance their work through what they were doing. We'd start the next day with a small group discussion of what they had worked on their own, in which they would present their findings to a small group of people, and then we moved into whole group processing again. Later in the course, I talked a lot less. We had less of the collaborative group work to discover things initially, and more of students doing that work on their own at home, coming in again and in small groups, presenting it to each other, and then processing it as a class in the whole. Now, the way that we organized assessment, because we want to try to determine that students actually are learning things on their own, is that I dispensed with major tests, except for the final exam. But we had a quiz every week on one of the 2 days that we met, not which day it was not announced. And that quiz was, with ample time, a problem a problem at the same level as those they had been doing for homework. Make a construction early on, prove a theorem later. Same level though, it was an authentic assessment in terms of what they were expected to do in learning geometry. Participation, early in the course, if they showed up, they got 2 participation points for the day. If they made a presentation, great. There was neither any urging that they make presentations, nor did they get an extra reward for making a presentation. That's a significant way in which this would differ from how we would do, for example, the analysis course, advanced calculus. Halfway through the course, I changed the rules of the game. In order for them to earn their 2 points, they had to contribute to the discussion, whether it's making a presentation or asking a useful question. If they showed up, they got 1 point. Some of the students thought of this as penalizing them. I took a point away from them. My point of view is they never had any to start with. By being there, they get a point, and by contributing to the discussion, they get a point. We also took seriously Dr. Clark's point of view that by the end of the course, they should all have a notebook in which all the theorems that we've covered, they have recorded a good proof of it. And so we had to check those notebooks while they were taking the quiz. And then there was a final exam at the end that was just a number of questions at the same level of what they've been doing in the course. We graded the notebooks. In the interest of time, I won't go over how we did that. But you can see there that it took various things into account, and there was always one problem that was graded very carefully. So now let me illustrate what I mean by figure versus ground. At a certain point in the course, not long after the students are moving from justified constructions, to proving theorems, they come across this sequence of theorems. This is not the complete sequence, but in particular the 2 that are highlighted in yellow. The base angles of an isosceles triangle are congruent. The isosceles triangle had been previously defined. And then this theorem a bit later, if 2 angles of a triangle are congruent, then the opposite sides are congruent. We all recognize that one is the converse of the other. The students don't recognize that one is the converse of the other. The first case is stated quite differently. They're not stated as 2 different if-then statements in language. And so that's when something came out of the ground. We had to discuss, we had to bring out of the ground naive logic and have a discussion of how these 2 theorems were related. Now this is only after the class either said this theorem had already been proved or proved that one again. So out of the ground then came this discussion of naive logic, and we managed to translate both theorems in a whole class discussion into forms where we could compare them and see that they were converses. At one point in the course, I was very surprised that the students failed. Nobody could come up with a proof of this theorem 2 class meetings in a row. And I did not think it was that hard a theorem. So they struggled with proving that theorem. And so this is another point, and that is that the assessment should take into account the student's readiness to know things and where they are. And so I changed the quiz that I had planned and gave them this problem as their quiz. And you'll recognize that I'm giving away the store. Right, I'm telling them what the key idea is to prove one direction of that theorem, because at that point it wasn't that I didn't want them to be frustrated. I thought that we needed to move on and break it down a little bit more finely, and so they were able to do that. But I probably did it too soon because that same day after the quiz, 2 of the students said they already had proved it and were ready to present it in class. So I just say this as a caution. Wait. You should always wait. You should do this sort of thing, but be sure you wait. We had a quiz rubric. It wasn't that the quizzes were right or wrong, but we tried to get the students to see what we were looking at in terms of how they presented things in their proofs. Some of this came up in the discussion, in the panel discussion earlier today, that they don't really know what to write. So we had something that they could refer to. The students did actually pretty well on the quizzes. The median grade in the class was consistently at a B level or higher on those weekly quizzes. And the final exam, the median grade was 44 out of 60. There was some a possibility of extra credit. There were people that had somebody that got a 64. I can't remember whether I took the 2 graduate students out of this list. I think I did, or the statistic. The final exam was was comprehensive in the sense that they had to prove theorems, they had to solve a practical problem, they had to produce a justified construction, at least the initial number, and then there were some others they could choose then to do something else, but from that list of problems. And then at the end, we asked them about the course, and probably got mostly what we expected. We asked them what they liked most about the course, what they liked least, what they had learned. And then the one I wanted to know the answer to is that I wasn't forcing them to present things for points. They could just ask questions. And they got as much credit as someone who made a presentation. And so I asked them a complicated question. Did the fact that points were not awarded specifically for presenting proofs in class affect the likelihood of your presenting proofs? That was too complicated a question. So I can tell you, we decided to analyze the responses somewhat differently. 23 students out of 26 students took the survey. 2 of the students had already dropped the course out of the 26. So we were down to 24 anyway, and I think that one was just absent when I gave the survey. So we looked at their responses in terms of what did they speak positively about and what did they speak negatively about in their responses. About a quarter of the students liked the idea of the group work. They liked the idea of presentations. Am I 2 minutes over, or am I okay?
You're okay.
Okay. Only about an eighth liked the structure of the material. Only about a third mentioned the positive environment, meaning the respectful environment that we tried to create in the class. A number of students objected to the level of the course difficulty. About an eighth of them did not think the instructor was helpful. And about a quarter of them did not like the idea of making presentations personally. But then they weren't obligated to, remember. So when we look at the cons and pros, other notable trends, a number of them did not understand why we were forcing them to do proofs, even at the end of the course. So you don't reach everybody. About an eighth of them were concerned about being frustrated. They thought the proof process was hard, really. On the other hand, almost half disliked the course structure, but now compare that. At the bottom of the other side, 15 out of 23 said that it changed and challenged how they thought about problems, and a like number thought that it improved their proof-building skills. So this is pretty much what I expected. I expected a split. I got a split in the attitudes of these students about the course. So while that's up there, and we're looking at a picture of Dr. Moore, let me tell you why I decided after many years to go ahead and undertake teaching the geometry course, which I had not shown any inclination to do. I think that we need to change the way we teach many of our math courses, and in particular, those that are taken by future teachers. And so the geometry course, as Dr. Clark suggested, is going to be my training ground for other teachers in our department who are willing to embark on this course with me. And with the connivance of the chairman of the department, so that the faculty who embark upon this will be rewarded. I now have 3 junior colleagues who are willing to embark upon changing a number of our courses from standard lecture to inquiry-based. And so geometry will be the training ground, then we'll knock down abstract algebra, and then we'll knock down linear algebra, and we already have advanced calculus. That's 4 major courses that would be taken by all high school teachers that will be on an inquiry-based footing in the next couple of years, I hope. That's the plan. Thank you.